Hi. In this video, we're going to talk about different ways to represent acceleration. The first way is through something called dot diagrams. Dot diagrams are snapshots of an object's position, with each snapshot taken over equal intervals of time. The object is represented as a dot. So our first example, we have two marbles. These marbles are represented by these dots here, and they're going at two different speeds. And I know that because this is the first snapshot. I wrote a 0 to represent a time of 0. So when we first start out, the two marbles are at the same position horizontally along the same number line here. They're at the same position. But then as time goes on, after 1 second, the first marble moves a little bit, the second one moves a little bit further. 2 seconds, 3 seconds, 4 seconds, 5 seconds pass, and each of these dots represent an equal interval of time, in this case 1 second each. And so it looks like the marble at the bottom here is moving faster because there's more space between the snapshots. Second example of a dot diagram is, let's say you're going on one of those drop towers, like the carnival, they raise you up and then drop you. So you start up here at the top at time 0. You start falling, you don't move very fast in the first second, you go a little faster, 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 so you're increasing how much distance you're covering each second, so you're getting faster and faster. This is speeding up. And then let's say you have a skateboard that's just coasting on its own down the sidewalk. This is example 3. It starts out going fast, but then friction slows it down, slower, 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 and then it comes to a stop here at 5 seconds. And so this is a slowing down example. The second example is velocity time tables. So in these ways of representing acceleration, we have the time and the velocity at each time. So example 1, at a time of 0 seconds, we have a velocity of -2 meters per second. So we're moving at 2 meters per second west. Remember our velocimeter. So starting out at a -2, and then over time that goes to -4, -6, -8, -10, ends at -12. So we are speeding up, and you can see this is an average acceleration of -2 meters per second each second. So we're jumping 2 each time. We're going 2 in the negative direction, so that's our acceleration. Example 2, we start out at 18 meters per second positive, and then we start, as time goes on, it goes to 15, 12, 9, 6, 3. So here we're slowing down at a rate of -3.0 meters per second per second. And then example 3, if you look at the velocity here, at the start, it's 5 meters per second. After a second, it's 5 meters per second. After 2 seconds, it's still 5 meters per second. It stays constant. So this is an acceleration of 0. The velocity is not changing, and so we say this is constant speed. All right. And the third way of representing acceleration is maybe the trickiest, and that's with motion graphs. So with motion graphs, you can use both position and velocity time graphs. And for each of these, there's some tricks that come with it. So let's look at the first example. If you're speeding up and you're moving in the positive direction, on a position versus time graph, that looks like this, where you're starting out going relatively slow, not much change in your position, but then as time goes on, you start jumping further and further up. So you're speeding up, starting out slow and going faster. We represent that on a velocity time graph by starting out very close to 0 over here, and then over time getting higher and higher, representing a more and more positive velocity there. So we get faster and faster. Example 2 is the same thing, except now we're moving in the opposite direction. So instead of going up and to the right, now we're going down to the, instead of going up, now we're going down. We're always going to the right because time is always going forward. So now we're going down on this position time graph. We start out not moving down much at all, so it's very slow at the beginning. Then you can see some gradual change. It's getting a little bit faster, and then at the very end, it's sloping down quite a bit. And so we represent that on the velocity graph, starting out very close to 0 again. And we're getting a little bit further from 0, further, and then at the very bottom here, we're pretty far from 0. We're going very fast in the negative direction. Example 3 is pretty straightforward. It's a constant velocity. So I drew this line wrong. I just realized that. Do you see my mistake? I drew this object at rest, which I guess I did draw at rest over here too. So there's different options for this one. I was imagining when I originally wrote this, I was going to do a constant velocity like this. And that would mean that the velocity time graph part would look something like this. So any flat line for the velocity time graph. Sorry for the confusion on that one. Let's look at a few more examples of motion graphs. So what about slowing down? What would that look like on a motion graph? So when something's slowing down, that means necessarily it started out fast. If you're going to slow down, you have to start out going fast. So starting out fast means you have a very high slope at the beginning, and then it gets slower and slower. In this case, we're going up, so it's in the positive direction. So we start out with a high positive velocity and then get slower and slower and slower. This looks a little weird on the velocity time graph at first glance, but stay with me. We start out with a very high velocity, so we're very far away from zero. So we start out very high, and then we go slower and slower and slower, getting closer to this zero velocity here. If we hit this bar right here, that means we have stopped. We hit zero velocity. So we're getting slower and slower and slower. Final example here, slowing down in the negative direction. We start out going fast at first, again, and then we get slower, 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 almost stopping here at the end. So this is going to look basically the mirror version of this one, where we start out with a negative velocity this time, but it's very fast. We start very far down in negative velocity, and it's going to get closer and closer to zero, closer and closer to rest. So that's all I've got for you in this video. Remember, everything you have is a gift.